In the previous module, we began studying the problem of two-level combinational synthesis by introducing a simplification rule. When iteratively applied to the first canonical form of a Boolean function, this rule allows us to simplify logical expressions to obtain a minimal form. However, we encountered several challenges in applying this rule directly to expressions. The Karnaugh's method shifts the problem of two-level combinational synthesis from the algebraic domain, where expressions are manipulated directly, to a geometric and topological domain. This method is based on a table called the Karnaugh map, which is an alternative to the truth table for representing a Boolean function. The Karnaugh map allows for an easy and visual identification of pairs, or more generally, groups, of minterms at a Hamming distance of 1, on which the simplification rule can be applied. The Karnaugh method is a graphical approach that systematically addresses all the questions posed at the end of the previous module, which can be summarized as follows. How do we identify prime implicants? How do we select the necessary prime implicants to construct the optimal solution? In this module, we will study how to construct a Karnaugh map, and in the next module, we will discuss the algorithm for combinational synthesis using this map. Previously, we studied how to represent a function using a truth table or using the onset, the offset, and optionally the don't care set, which we will not consider for now. A Boolean function with n variables can also be described using a Cartesian representation in an n-dimensional space, where each axis represents a variable. Since each variable is binary, it can take only two values, 0 or 1. The result is an n-dimensional cube, or n-cube. Each vertex in the n-cube represents a point in this n-dimensional space characterized by specific coordinates, meaning the values of each binary variable and the corresponding value of the function. Let's look at an example. We consider a function with 3 variables and the onset listed here. The representation using a truth table is already familiar to us. Now we can move on to the representation in a 3-cube, a 3-dimensional cube. We see the 3 axes, each assigned to a variable. Each vertex of the 3-cube is labeled with its complete coordinates. The first bit corresponds to variable A, the second bit to B, the third bit to C. Additionally, we have adopted a graphical convention. A black dot represents a vertex where the function evaluates to 1. A white dot represents a vertex where the function evaluates to 0. Finally, I'd like to point out that we have connected only adjacent vertices where the value of only one variable changes. This aspect will soon prove to be very useful. Another very interesting aspect of this representation is that an n-cube can be obtained by projecting the representation of an n-1 cube into a new dimension, that is, onto a new axis. Let's start with a 1 cube. This consists of 2 points in a one-dimensional space with coordinates 0 and 1. Now, the 2 cube can be obtained by taking the 1 cube and projecting it onto a new axis as shown here. The coordinates of each vertex must now be encoded with 2 bits. Before projecting, we append a 0 to the left of the previous encoding of the 1 cube. After the projection, the 0 is turned in a 1. We can then repeat the same procedure to transition from a 2 cube to a 3 cube. We add a new bit to the left side of the configuration of the 2 cube with value 0. Then, we project it forward to form the 3 cube and we turn the 0 in each projected point in a 1. In theory, this process can be extended to an arbitrary number of dimensions n, although graphically representing higher dimensional n cubes becomes increasingly complex. An interesting aspect of the Cartesian representation is that every pair of points in the n cube connected by a segment is at a Hamming distance of 1. This makes it easier to identify pairs, or more generally, sets of 2 to the power of n minterms, on which the reduction rule can be applied. Indeed, an implicant is a sub-n cube contained within the function's n cube, consisting only of points where the function value is 1. Let's revisit the example of function from earlier, along with its corresponding Cartesian representation. In green, we highlight an implicant that groups together 2 minterms, forming a 1 cube. We can expand this implicant to include the 2 minterms on the right, forming a 2 cube with 4 minterms. Indeed, the application of the simplification rule on sets of minterms corresponds to identifying n cubes containing only one valued points. We can see that this 2 cube cannot be further expanded. Therefore, it represents a prime implicant. Here is another prime implicant that covers 2 minterms. Finally, we notice that the point 101 is shared between the 2 identified prime implicants. This means we have implicitly applied the idempotence property. The Cartesian representation becomes difficult to handle even with just 3 variables, and even more so as the number of variables increases. For this reason, it is more convenient to transition to a 2D representation by flattening the n cube onto a plane. Specifically, we unfold the n cube with 2 to the power of n vertices onto a table with the same number of cells, forming the so-called Karnaugh map. We assign each function variable either to the rows or to the columns of the map. The set of variables assigned to the rows defines the row index, while the set assigned to the columns defines the column index. Finally, each cell in the Karnaugh map contains the function's value, either 0 or 1, when the variables take the values corresponding to the cell's coordinates. Let's start building the Karnaugh map in the simplest case, that is, for functions with only 2 variables. In this case, the 2-dimensional grid can be directly superimposed onto the 2 cube. Let's consider an example. Take the function with 2 variables, a and b, and an onset composed of minterms 1 and 3. The corresponding Cartesian representation has 2 axes, the vertical axis associated with variable a and the horizontal axis associated with variable b. We can then overlap a 2 times 2 grid onto the 2 cube using variable a as the row index and b as the column index. For the 2-bit coordinates of each point in the 2 cube, we use the first bit as the row coordinate and the second bit as the column coordinate. We complete the map by replacing the vertices of the 2 cube with the corresponding function values indicated by the coordinates of the vertex. Finally, in the case of the 1 cube, which has limited practical use since it corresponds to a function with only 1 variable, the Karnaugh map can be equivalently constructed with a structure of 2 columns and 1 row, or vice versa, 1 row and 2 columns. The Karnaugh map for a problem with 3 variables requires the development, that is, the unfolding, of the 3-dimensional cube onto a plane, which is a 2-dimensional space. This results in a map with 2 rows and 4 columns, or alternatively, with 4 rows and 2 columns, depending on how the cells are organized. We will consider the first configuration in this presentation. To preserve the adjacency between the vertices of the 3 cube, the unfolding requires that the columns are not numbered sequentially, but with a gray code, so that each column is at a Hamming distance of 1 from the previous one and the next one. Therefore, the columns are numbered as 00, 01, 11, and 10, essentially swapping the last 2 configurations. Finally, with the map having 2 rows and 4 columns to calculate the coordinates of each cell, we assign 1 variable to the rows and 2 variables to the columns. Let's consider an example. As you can see, we cut the 3 cube at 2 points and unfold it horizontally, obtaining a map with 2 rows and 4 columns. A represents the row index, while BC represents the column index. Now let's analyze the 2 cube in the background. The point 0, 0, 0 with value 0 corresponds to the first cell at the top left. Then 0, 0, 1 is the second, and in this 3-bit code, we separate the first 0, representing the value of A, thus the row index. From 0, 1, the values of B and C, which together represent the column index. We then complete this cell with the function value for 0, 0, 1, which is 1. Following the path on the 2 cube in the background, after 0, 0, 1 comes 0, 1, 1. As we noted earlier, the column coding is not sequential. Indeed, after the column 0, 1, there is the column 1, 1 at a Hamming distance of 1. We insert the value 1 in the cell. Finally, the last vertex is 0, 1, 0. We separate 0 from 1, 0, obtaining the coordinates of the last cell on the first row. Once again, we note that this cell is at a Hamming distance of 1 from the previous one. Additionally, by carefully analyzing the cut on the 3 cube, we can see that we are removing two edges between two pairs of points at Hamming distance equal to 1. This leads us to observe, as can be seen from the column numbering on the map, that the last column is adjacent to the first one. Indeed, we move from the index 10 to 00. We can apply the same reasoning to the second row of the table, which corresponds to the 2 cube in front of the one we just analyzed. The unfolding of a 4 cube onto a two-dimensional plane requires multiple cuts. This results in a 4 times 4 Karnaugh map, where we use two variables to index the rows and two to index the columns. Let's take an example of a function with 4 variables. Here is the Karnaugh map. For simplicity, we omit the representation of the 4 cube. The procedure to populate the map, which might now be a bit more laborious given the 4 variables, is as follows. Take each value from the onset, convert it to natural binary form using 4 bits, and use the first 2 bits as the row index and the last 2 bits as the column index. Then, put a 1 in the corresponding cell. Once all the onset elements are filled, the remaining cells, which correspond to the offset values, can be filled with 0. Additionally, we note that in this case, not only the columns, but also the rows use gray code numbering, so that each row is adjacent to the 2 neighboring rows. We can continue constructing Karnaugh maps for functions with 5 and 6 variables. However, in this case, since we've already established that on a single axis we can place at most 2 variables, we need to stack multiple tables in a third dimension. Beyond this point, for a higher number of variables, the approach becomes practically unfeasible. To conclude, we have studied how Karnaugh maps are constructed and analyzed their characteristics that allow for the easy identification of min-term sets to be reduced. In the next module, we will conclude the discussion by explaining the method that allows us to perform combinational synthesis using this representation.